All right, hello and welcome to the Off by One Security stream on this Saturday, September 14th. I know we normally do them on Fridays, but Alisa is in another part of the world and wanted to make sure this is the best opportunity for her to present. So welcome everyone. Thank you so much, Alisa, for joining me here. So many people have been asking for you to come on and do a stream, which I was delighted that you accepted. And yeah, so I want to start off the topic. I'll let Alisa explain it in much greater detail, but we're going to be looking at fuzzing and some interesting and different fuzzing concepts and principles than I'm sure many of you have seen on the stream before. So I guess we'll start off. Alisa, if you'd like to first give a little bit of background about yourself, that would be awesome.
I'm a security researcher and entrepreneur. I have been doing security research for many years now. I learned assembly programming at the age of 15, and then malware analysis, then vulnerability research, and so on. I'm the founder of the Zero Day Engineering project, which is a training project specialized in courses in vulnerability discovery and exploit development. And I'm also a winner of the Pantone competition of 2021. Oh, that's the basics.
Yeah, I saw that, the Parallels Escape. That was awesome. What kind of training, so actually, where is your training offered?
The training currently is online. So actually, currently I'm offering only self-paced courses, but I think I'm going to resume online training soon.
Oh, nice. And I'll get some links posted up about that shortly. So I guess tell us a little bit about what you're going to talk about today.
Today, I want to talk about fuzzing from first principles. So we're going to look really deep into how it works. And also, I want to introduce theoretical model and approach, which will help us to really understand very deeply how it works and how it can be improved from the ground up. I will also show some examples of my past fuzzing projects to illustrate how exactly it can work.
Nice, because yeah, that's one of the things people ask most of all is so many times you see a class or you see a presentation on YouTube or wherever where the bug has already been discovered, and so many people are like, well, how do I find the bug and how do I know if it's exploitable? So it's definitely a topic folks are interested in. I saw recently on your Twitter that you were taking a look at that IPv6 TCP/IP remote code execution. Any luck with that one?
Yeah, I was looking at it for a moment, and actually, I think it's more interesting that it's currently published, so I'm going to look more into it.
Yeah, I took a brief look at it, but I got a little bit spooked by other folks saying that the challenges around making sure the packets are all lined up in a specific way on a busy system and how they're, from what's been shown so far anyway, there are some requirements where you need to disable some services or have a non-busy system or something like that. So I'd love to see some progress on that one for sure.
Yeah, actually, it's a related topic to what I will be discussing today. Basically, in the program, there are many constraints, and today I'm discussing how these constraints impact what we are getting out of fuzzing in the context of fuzzing. So the same kind of constraints, they exist during exploit development. And this bug in particular, the constraints are quite tough, which is why currently people only were able to demonstrate a crashing POC, and there is no publicly developed remote code execution exploit for it.
Yeah, and one of the surprising parts was the 9.8 CVSS score, and then it was also rated as low complexity. I think that might be a little bit misleading, but hopefully you'll find something sooner. I saw also on your Twitter, I wanted to ask this one. It was about spill the register bug theory. Can you explain that a little bit?
I was referring to one particular vulnerability that was recently exploited in Google Chrome, specifically in the V8 engine. And I think it was patched just in August, and it was a very interesting bug chain because it was chained together with a vulnerability in Windows kernel to escalate privileges from the renderer exploit after remote code execution and to escalate privileges. This bug is also quite interesting, and it attracted my attention because it is a subtle bug in how compiler works, and specifically in WASM compilation. So there is quite a lot of contextual theory that is required to understand it. And basically, what I wanted to show is the general direction of where to look at if people want to understand how this bug works, because it's not obvious from the ground up. So there is some background reading and background theory that can be explored further in order to exploit it.
Nice. Yeah, V8 is quite complex. I saw as a blog maybe in the last 6 months from Exodus Intelligence going through an amazing V8. I think it was either type confusion or USAFT free, but the complexity. I've seen some classes out there just specifically in V8 internals because there's so much knowledge you have to have just to even approach that area. So
yes, normally, when you're looking at V8 bugs, almost every single vulnerability requires a completely new set of knowledge. I mean, even if you're already experienced researcher in the JavaScript engines, or if you're even a developer, almost every vulnerability introduces something new that you look at the code and you don't understand what is going on there. So even advanced researchers, they have to look up more theory, and each time it's like a new learning process, which is part of why it's so exciting to attack JavaScript engines.
yeah, absolutely. And I mean, as I'm sure you know, the bug bounties, especially from exploit acquisition companies, has gone up astronomically compared to what it used to be. I used to sell a ton of exploits back in like 2013, 14 against IE and Edge, and you only get $30,000 for them maybe, and nowadays it's like $500,000, which is amazing.
Yeah, absolutely. And in fact, this was, I predicted it about 10 years ago when I made a decision to, stay in the vulnerability research industry and stay in the hard topics, despite I realized that browsers getting more complex, and it's like really hard area to work in. And also I realized that the bug bounties will be growing. There will be more bug bounties introduced, and their cache outs will be also growing. So and at that moment, I decided to invest more time into more universal approaches to bug hunting. I hope that today I can show a little part of my thinking, of my mindset in that regard, because I always try to find some sort of universal approach so that I will not be constrained only in one target for attacking, such as only in browsers or only in hypervisors. And so currently it's quite exciting time for security researchers.
Yeah, I'll ask one more question because a couple of folks have already asked, and I know that this is a topic that comes up every single time I have someone who's an expert in exploit development. I guess it's a two-part question, but it's basically, do you see the world of binary exploitation coming to an end anytime in the near future? And also, do you see AI playing or machine learning playing a major part in like your research around fuzzing and exploit development?
But the binary exploitation, of course, is not going to go anywhere. First of all, software exploitation is not constrained to binary. We know that many binary programs nowadays are actually underneath. They are more like web applications. If you think about Microsoft Teams, for instance, which is written in .NET, bugs there are not binary, but they are still vulnerabilities, and the exploitation is still follows the same rules. So my personal mindset is that I'm focusing on software exploitation. I don't constrain myself like I'm only binary or I'm only in the web applications. And specifically to binary, I think this area is not going to disappear for sure. There are many reasons why is it so. There is legacy code, there is inertia in software development and deployment. I mean, just think about that many companies are still using Internet Explorer like a lot. It's much more than we think. Meanwhile, Microsoft isn't even accepting Microsoft Explorer bugs is valid. But still, in the real world, it is a huge industry, and vulnerabilities in it are still kind of valuable. This happens because of the inertia in the corporate processes and in the society in general. And this inertia, it is rooted in many different reasons. So it's not going to happen overnight, like Rust suddenly occupies the whole world and all the software is written in Rust. And Rust has its own problems, but this is a different topic. What I want to say is that binary exploitation is going to stay, except that the focus will change, of course, of what the most popular target areas would be. There would be probably more of a web application style bugs in software which is developed in more high-level languages like .NET. But yeah, binary exploitation is not going to disappear completely for sure anytime soon. And about the second question, obviously AI is currently revolutionizing everything, and this is not so much overhyped. I'm currently looking at it quite actively, specifically various applications of large language models to fuzzing and to code analysis, to static code analysis for vulnerability discovery. And the potential is huge, but also there are specific challenges that have to be solved before this can become productive and useful. And the thing is, those challenges are of fundamental nature, meaning that in order to leverage LLM, for example, for bug hunting purposes, we will have to solve fundamental problems of LLMs, such as hallucination and so on and so forth, which makes it hard because people who will try to use these tools to apply to vulnerability research, they do not have the specialized low-level knowledge in LLMs and research experience in that particular area. So this is going to be maybe not very fast, but definitely it will change a lot. And it's already changing. Another problem in this area is that actually the inertia of human consciousness currently is one of the stopping factors, because even when you have already tried ChatGPT or Perplexity, applied it to some reverse engineering workflows, just analyzing some code, and still, in the next situation, you fall back to the same old ways of doing things because you're not accustomed to using these things. They accelerate so much, they are so effective, and it's also moving forward so crazy. So this kind of human consciousness is a little bit of a stopping factor. And I think that just reminding people that they need to learn to use these tools and actually apply them in their workflows is already an important thing to move forward in this.
Yeah, absolutely. And I'm sure you looked at Project Naptime and they've made some pretty interesting progress, but even they said, with Google Project Zero, it's a long way to go before we are even going to think about the idea of machines replacing humans in terms of vulnerability research. So excellent thoughts. So I'll go ahead and let you get started here. I know folks are dying to have you go through this, so I'll let you take it away.
Okay, so I want to start my presentation with a little reality check. We know that Google has a huge, massive fuzzing cloud with tens of thousands of fuzzing instances, or maybe more, I'm not sure. And it's fuzzing its own software, such as Chrome browser and V8, continuously. Those browsers are supported. Meanwhile, researchers consistently come up with new 0 days in V8. And looking at those 0 days, there is a way, looking at the bug, to estimate whether it was found by fuzzing or whether it was found by manual analysis. And looking at those bugs, I can say that many of them were actually found by fuzzing. Moreover, I recently heard in my Twitter feed, somebody mentioned that one of the bugs that they recently submitted to V8 bug bounty was found by fuzzing. So if you're following the mainstream hype about fuzzing scalability, scaling, more machines, more scaling, parallelization, more smart fuzzing, and so on, then this situation doesn't make sense, right? If Google has such a huge fuzzing cloud, then how is it even possible that researchers still come up with new vulnerabilities found by fuzzing? But today I will show you that this makes actually perfect sense. And in fact, we can leverage the kind of theoretical thinking that I'm trying to present today in order to outsmart Google Cloud, for instance, because this is what we need to do if we want to find new vulnerabilities. This is our adversary, and if we want to participate in bug bounties. Next thing is I want to challenge the concept of the smart fuzzing. Normally, when people talk about smart fuzzing, the meaning is coverage-guided fuzzing, modern tools, scaling, parallelization, various cool approaches like augmented with concurrent execution. But this is not necessarily smart in practice. And ultimately, smart fuzzing comes down to understanding what is going on from the first principles, understanding what you're doing, what your fuzzer is doing. And once you're able to understand it, you can easily shift away from this little box of, current fashion. This is coverage guidance, this is scaling, it's fashionable, it works. You go out of this box and think in a totally different direction, and you're able to solve the problem in the most efficient way. To understand the first principles of fuzzing, we want to look at the program in the same way as the fuzzer sees it. Ultimately, fuzzing is simply sending random inputs to the program. And you have to understand what is going on the lowest levels. Every program can be represented as an infinite flow of CPU instructions, which is branching. Here is a little bit romanticized picture of branching tree. In practice, it will be more boring and more complex. The basic idea is that you probably seen the abstract syntax trees. This is similar but not the same. In this kind of tree, we disregard all types of nodes except for the conditionals. So whenever there is a conditional statement in the program branches. There may be 2 branches or more branches. And this infinite branching is like infinite flow and infinite flow of branches. So in this kind of visualization or model, we only care about this kind of conditional statements and nothing else. And in order to pass one branch, you have to satisfy a specific condition. Imagine that you're sending an array of 10 bytes, and the first byte must be a particular value to bypass the first branch. And now somewhere on the branches of this tree, there is a vulnerability. So our challenge, actually, and challenge of the fuzzer, is to traverse the tree by satisfying all the conditions of the branches so that it eventually reaches the vulnerability. This is how we are going to think about fuzzing on the low level. Before I proceed to demonstrate how it applies, I want to give a little introduction to the mathematical tool that I will be using today, which is probability theory. Probability theory is similar to statistical analysis, except it is reversed the other way around. So statistical analysis is applied to the past arrays of data in order to analyze it, derive some patterns, while probability theory applies to the future and allows us to predict events. And the key distinction is that probability theory does not require a sequence of events in order to work out. Where statistic analysis, it requires a sequence, and it can count how many events in the sequence and calculate probabilities and so on. In modern probability theory, we can take just one event and we can predict the probability of this event happening, even if it's not going to happen ever again. This is the key difference. Both probability theory and statistical analysis share the same theoretical foundation, but their applications are very different. The probability that we're interested in is called Bayesian probability and is distinct from frequentist probability of the statistical analysis. Probability theory, I'm not going to go very deep into it. I just mentioned briefly that this is currently the mathematical model which underlies both AI, machine learning, and the physics itself at the lowest level. So basically, to the best of our knowledge, the field of probabilities is the nature of the universe. But without going too deep, I'm just going to cover a few basics. Probability theory, it has 2 sides that are relevant to our further discussion. First is, what is a probability? Given a random variable, x, that can assume various values. A probability is a rational number within the range of 0 to 1, which represents the likeliness of that variable taking this specific value. In such a way, for example, we have a variable, it takes in some values, and we say that the probability of the variable taking the value 10 is, for example, 0.1, which means 10%. And we have a certain expectation that when this event happens, or the variable takes the value, it will, in in 10 out of 100 tests, it will take this particular value. Probabilities also can be joined together. We can consider different independent variables and evaluate probabilities of independent variables. For example, we have a buffer, and the fuzzer will be fuzzing this buffer of some limited size, maybe size of 10 bytes. We have the first byte, which takes some value, and the second byte, which takes some other value. Both values will be checked in the program. So this would be like our two independent variables that we will need to consider. Another side of probability theory is the concept of probability distribution. It is an abstract object or a measure of representing how exactly probabilities of a particular variable are distributed. Probability distribution is usually represented for discrete variables with probability mass function. It is a function which takes in as the domain all possible values of our variable, and for each of these values, it outputs the respective probability of that particular value of the variable taken of this particular value. A simple example is a uniform probability distribution. Let's say that you have a variable that can take values from 1 to 10. And in this situation, the probability of each value, if this is a random variable, the probability will be 1 out of 10. And here is a couple of examples of common probability distributions. The first one is the uniform distribution, which I mentioned previously. This just reflects that the different values of the variable are equally probable, equally likely to be assigned. And another popular distribution is a normal distribution, which governs most of the things that happen in nature. Here it is weighted, and a certain medial range of values are more likely to happen, while smaller values and larger values are very low likely to happen. So a value is guaranteed to happen if it has a probability of 1, and it never happens if it has a probability of 0. Various values in between represent the degree of likeliness of how this value happening. Now, with this in the background, let's take a look at a very simple example of a program. Here, this is a rudimentary program that does the following. It accepts 1 byte on the input vector. If that byte is equal to 42, it will print a message, and if it's equal to 0, it will lead to software vulnerability. Other inputs are invalid. And what happens during fuzzing? Let's assume that we are throwing random bytes at this input vector. The first thing we want to see here is the probability of the fuzzer reaching each particular branch. The probability of this one branch, as shown here, will be around 4%. The probability will be 0.039, which is around 3.9%. And the probability of this variable passing the second branch is also 0.039. So here we have equal probabilities. This is what happens in real life when we are fuzzing this simple program with some ideal random fuzzer. Now, another thing I want to say here on this simplified picture is the success rate of a fuzzer. What is a success rate? A success rate is that fuzzer either discovered a new branch or found a vulnerability. Or now, in this particular scenario, I model it as that the fuzzer was able to find a particular branch here. There is 1 byte can take values from 0 to 255, which means that maximum, the fuzzer will run 252 times before it hits the correct number. In practice, of course, the fuzzer is random, so it will not run 255 times, but rather it will be the number of times somewhere in between 0 and 255. We can imagine that if you do it many times, the number of tries will average out, and we can say that the fuzzer will need to run about 127 times before it finally reaches finds the correct value here, which means that the fuzzer success rate is less than 1%. Here is the calculation here. It's specifically 0.79. And we're talking about 1 byte here. Another thing that I'm interested to see here is the error rate. The error rate is the opposite of the success rate, which in this case, it will be slightly more than 99%. So this is kind of the minimal percentage of failures of any fuzzer. Here, of course, I'm showing a very simplified picture. This is just 1 byte specifically. A real fuzzer, it can fuzz maybe words and double words, some other values. Based on this 1 byte precision, somewhere in the average, the fuzzer's error rate will be always around 99%. This is like, it's normalized, actually. It's normalized in our community that it's normal, but I don't think it's normal. The next thing that I want to see here is timing. So based on these numbers, you can actually calculate the time that you need for the fuzzer to find this particular branch that has a vulnerability. For example, if your fuzzer is running at 100 cycles per second, and it throws random numbers at this 1 byte, then in 1 second, it will find the vulnerability. Now, here is how this same picture looks from the perspective of the program. From the program's perspective, the probability of each value is 0.5. Like 50% is 42 and 50% is 0. I think this may not make a lot of sense currently, but hopefully it will be clear later. Because when we're looking from the fuzzer's perspective, it will be throwing all those random bytes. And from the program perspective, it considers all other inputs invalid, and it's only concerned with specific valid inputs. Now, this was a very simple picture, and now I'm going to extrapolate it to a more complex example. What happens when our program keeps branching on? What happens with all those probabilities and error rates? I want to see. The general rule here is that probabilities will compound, and basically the probability of discovering each following branch will be lower and lower and lower. This directly follows from the probability theory that I mentioned in the previous slide. So in the case of this slide, the second order or second layer of branches will have a probability of, this is a very small probability, around 0.15%, in contrast to 3.9. And as our tree keeps growing with each branch that our fuzzer attacks, the probability of finding both values correct, it will be lower and lower and lower. This is what generally happens in the program. What happens to error rate? The error rate will be also growing, but somewhat slower. So while the probabilities are really dropping exponentially, the error rate still grows, but somewhat slower. It always seems to be around 99% and tending to 100%. So the overall trend in a complex program is that we have an exponential loss in general. The probabilities of finding next branch are diminishing and diminishing. So this is a very ideal example. How it really works in real life, it will depend on many, many factors. The width of values that we're fuzzing, the specific techniques that are being used, and so on. So here I want to demonstrate how it works in general. Now I want to apply this and take a look at how actually these numbers look for specific situations, specific fuzzers. Here I look at a simple random fuzzer, but I take a more specific situation, a more realistic situation where a fuzzer will fuzz some large array of values. Imagine you have 10 bytes and your fuzzer is just fuzzing all this huge array. What happens here? The first thing you can notice here is that because the fuzzer will go through a larger number to fuzz it, larger array, the probability of discovering a branch randomly dropped significantly. It's like super tiny. It's 1 second to the power of 80. I have no idea what kind of small number is it. And this kind of probabilities, as we go up the tree, they still will be compounding and will be lower and lower and lower. Which means that if we're using this kind of purely random fuzzing, basically it will be stuck at the initial first levels of the branches, and it will never proceed to higher levels. So something like this will happen. Here, the white is the part of the tree that our random fuzzer would be able to cover realistically, and the gray branches will be never discovered in meaningful time. This is what happens with purely random fuzzing of fairly large values. And this was the reason why coverage-guided fuzzing was introduced, to solve this problem specifically. So how did it solve it? Let's look at the next picture. Here I'm looking at this model from the perspective of a coverage-guided fuzzing in the branch discovery phase. So basically, there is few things that stand out in this situation. First thing, there is still a low probability of discovering each branch. In this situation, it is still around 0.039. Then it starts compounding and compounding, even in this simple example with just 1 byte values, even for a coverage-guided fuzzing. The only real thing that the coverage-guided fuzzing added is the ability to save a successful test case that will effectively collapse the probability of passing some branches to 1. Another thing that I see here is that there is still a 99% error rate, which is growing, which means that even if you're running a smart coverage-guided fuzzing, your fuzzing still runs those empty cycles 99% of time. And it still has a low probability of discovering the next branch. So how does this whole thing grow? I think I had a separate slide, but okay. So the point here being is that because the tree keeps branching, the probabilities keep diminishing. The fuzzer will be still losing approximately exponentially. The loss will be approximately exponential, but maybe not so fast in the purely random situation. And this, by the way, is the second stage of the coverage-guided fuzzing, when we have already discovered all the branches, and now we're just running through these branches with some fuzzing data. So we're not supposed to discover any new branches, but just find some vulnerability which sits on one of the branches. So what's going on here? The first thing is that saving a successful input sets the probability of passing some particular branches to 1, which means that our probabilities is significantly improved, and overall the process will be faster. Here, the probability of finding the next branch is also better because it doesn't have to compound with the previous one. And probably the most important thing in this model that I noticed is that fuzzer costs they seem to be approximately linear. They're not exponential anymore. So when your fuzzer has already discovered all the possible branches and it just keeps running through the inputs to find the vulnerability, at this stage, it will be like this. it will be running in a stable way. The error rate will be still high, around 99%, but more or less stable, and it won't, there will not be this kind of exponential explosion that we have to deal with in fuzzy complex programs. But still there is a high error rate, and still there is some low probabilities. So my point here is that I don't want to discount fuzzing or coverage-guided fuzzing. It's not even possible to discount, honestly, because it's so successful and there is a track record. My point is, if something's so unproductive, like a process that fails basically at least 99% of the time, and that keeps losing exponentially, if that can be so successful, then what could be possible with a really more intelligent approach? Now, with that low-level picture in mind, so last notice is that in a real-life program, of course, there will be much more complexity. I hope that you can extrapolate further these branches, and you already can see how exactly these probabilities will add up in various situations, whether you're fuzzing the program with a random fuzzer or with a coverage-guided fuzzer. The important things about coverage-guided fuzzer is that it will still have a high error rate, and it will still have those low probabilities of discovering the next branch that will compound over time, which means that even for a coverage-guided fuzzer, it will have some issues traversing further and further down the tree, because it's it loses its efficiency exponentially, is what I'm seeing from this model. Now, with this low-level picture in mind, I want to step back and look at this situation from a very, very high-level perspective. Consider the program or the fuzzer in a four-dimensional relativistic space-time. Forget about time, that fuzzer runs in time, that it produces inputs sequentially, and just look at it as the whole fuzzer. So it started, you run it to the end, and you have this corpora of produced fuzzer inputs. Basically, over time, a fuzzer will generate a finite set of discrete values or inputs. It is finite because it is assuming that it is constrained by the size of the input that a program can take. Obviously, if you just run a fuzzer infinitely, then it would generate infinite inputs. But because we have a certain buffer to fill with it, then it's probably be a finite set. So looking at this set of all possible inputs that a fuzzer can generate, the probabilities of generating those inputs are, so there is certain probability distribution around those inputs. How likely is the fuzzer will be generating a certain input? And basically, we can model the fuzzer as a probability distribution. There is nothing else really. There is only the probability distribution, which represents the whole fuzzer. It encodes everything, the most important that we want to know about the fuzzer from the perspective of its results. Here I call it PF. This is the probability distribution of fuzzer. Similarly, we can think of a program as another probability distribution of inputs. Consider a set of all valid inputs to the program. A valid input can be defined as any input that passed at least one conditional statement, which is a validation. So there is this set of all possible inputs, which basically covers all possible branches in the program and all possible combinations of its execution. And this set, you can also think of it as certain probability distribution. Here I call it the PP. And lastly, we can consider a subset of the program inputs that actually lead to a vulnerability. This will represent a third probability distribution, which here I name it PV. This is a strict subset of the program's inputs, and it represents only those inputs that lead to a vulnerability. So here is, remember our first simple example of a program that accepts only one byte that can be equal to either 42 or 0. This currently is just a probability distribution of the fuzzer, which fuzzes just one byte. You can see that it's an ideal fuzzer. It's purely random and non-deterministic. So each value that it produces has an equal probability around 0.004. You can see that the values here from 0 to 256. This is the PF, or probability distribution of some ideal one-byte fuzzer. This is an example of the probability distribution of inputs of our program, of a simple program that can accept only one byte that can be set to either 42 or 0. So 42 and 0 are the two values that peak here, and everything else is null. All other values of the byte are illegal, and so they are not existing in this probability distribution. And lastly, here is the probability distribution of the vulnerabilities in that program. In this case, there is just one vulnerability, which happens when the target value is 0. The input value is 0. And the likeliness of this value causing a probability is 1. Now, in terms of this model, we can actually redefine the fundamental challenge of fuzzing. Our goal in fuzzing is to make the probability distribution of the fuzzer equal to the probability distribution of the vulnerability. Think about some perfect magical fuzzer. Imagine that each single input that it produces will cause a new vulnerability in the program, or find a new vulnerability in the program. This is what this particular statement represents. Currently, however, the real life is that state of the art on this is that the probability distribution of fuzzer is not even a superset of the probability distribution of the program, because a fuzzer is not guaranteed to generate every single input that a program can accept. There is a secondary goal here also, because we can think of this problem we can reverse it around and think of it in terms of the error rate. If we are able to reduce the error rate of fuzzer to 0, then effectively it's the same thing. We will reduce it to a probability distribution of the vulnerability. While currently the situation is that error rate is 99%, as I shown previously. So this is how we can model the fundamental problem of fuzzing in terms of this probabilistic model at the high level. Next, we can actually try to model fuzzing itself in terms of this model. This is just a rough idea. I basically just jotted it yesterday, jotted down, and I haven't thought it through. Basic idea is that fuzzing is some function which accepts the probability distribution of the fuzzer as an input, and it produces a certain objects, which is a practical measure of success of specific input values. We need this practical measure in order to optimize fuzzing. In this situation, we can optimize fuzzing. We can devise some sort of cost function and optimize fuzzing by letting the results array that was output of the fuzzing function, optimize it against first the probability distribution of the program, so moving fuzzer success closer to the valid program inputs. Then we can optimize it against those inputs that discover new branches, for example, and we can further optimize it to the probability distribution of vulnerabilities. This can be somehow implemented either algorithmically or whatever with machine learning. And then after this optimization, assuming that we have calculated the correct value of results, we can somehow reverse it and apply and calculate the correct probability distribution of fuzzer that will lead immediately to a better results in vulnerability discovery. This is just some basic idea of how it looks like. So this model that I show here, the meaning of this model is to guide fuzzing improvements, to guide our thinking and eventually to guide development of new techniques, be it on the low level or on the high level. On the high level, there are different ways how we can use this model to actually make fuzzing better. So as I mentioned previously, our goal is to make the probability distribution of fuzzer equal to probability distribution of vulnerability causing inputs. But this is a hard problem, obviously, otherwise fuzzing wouldn't exist. So instead of tackling directly the hard problem, we try to move toward it by looking at more trackable and less ambitious approaches. So the first approach it's trivial. We let the probability distribution of fuzzer tend to the probability distribution of program inputs. What this means in practice. If we fuzz the program based on valid program inputs, if you gather the samples that are known valid inputs of the program, then we already perform much, much better in fuzzing, because it allows us to skip this kind of exponential cost of exploring new branches, and we skip directly to linear phase of fuzzing known branches. But the basic idea I want to keep here, the thinking process, keep it abstract because it allows us to find a lot of specific technical solutions. So the basic idea is that we want to bring a fuzz probability distribution of the fuzzer closer to the probability distribution of program. This is approach number one. Approach number two, how to make fuzzing better. We can try to minimize the probability distribution of program. How is it even possible? It can be possible, for example, by I will discuss specific techniques later, but the basic idea is that the smaller the probability distribution of the program, the easier it is for the fuzzer to run through it and exhaust all possible options. And because the cost of running a fuzzer grows exponentially, so our goal is always to cut down this tree and keep it as small as possible. So the less branches, the better. The smaller, the better. It means that if we're able to carve out a specific portion of a program, for instance, we will have a much smaller probability distribution on it rather than fuzzing the whole program. And the basic insight here with this particular approach is that even random fuzzing with a small probability distribution of the program is more efficient than smart coverage-guided fuzzing of the entire program. I think this can be proved mathematically. I didn't attempt it here, but kind of in practice it holds. The third approach to optimizing this is try to get the probability distribution of the fuzzer closer to the probability distribution of the vulnerability. How is it possible? For example, we can let the fuzzer learn from past bugs. In this situation, the inputs that the fuzzer generates from such a probability distribution, they will be potentially attacking the same patterns or the same areas where previous vulnerabilities happen. This cannot be solved exactly because when we're discovering bugs, it turns out that the next bug is always novel. Well, not always, but sometimes it happens to be novel and something unseen previously. So, but we can try to get the fuzzer closer by letting it learn on the past vulnerabilities, and there's always this gap between what we can learn from the past bugs and what we cannot learn from it, but there's still vulnerability. And this gap in itself is also an opportunity, which, by the way, is a good opportunity for independent researchers who are forced to compete with the big fuzzing farms of vendors. And lastly, the fourth idea is to try to collapse the probability distribution of the fuzzer to one, to just finding the vulnerability. This is a completely crazy idea. It's theoretical, but kind of it seems like it works sometimes based on human consciousness alone. My point here is that the model allows for many solutions. There is many ways how we can play with it and use it to optimize fuzzing. And here I just showed 4 high-level examples that are encoded in the model. And most of them I can actually illustrate with my own fuzzing experience. And by the way, all the bugs that were found that were exploited at Ponto and Vancouver in this year were found by manual analysis. This is a reality check. So apparently, for purposes of adversarial offensive security research, fuzzing is so bad that nobody's even tried it. Actually, I hope that from the previous discussion, it's kind of it starts to make sense why actually sometimes even manual analysis or highly specialized dumb fuzzing can be better than a normal smart fuzzing. Now I want to go through my previous case studies of vulnerabilities to illustrate the specific approaches that I showed here. So starting from the first approach, pull the probability distribution of fuzzing closer to the probability distribution of the program. First, I want to say that the bugs that I will be showing here, some of them are very old, like from 10 years old. So some of them were found in the era when coverage-guided fuzzing didn't exist. But my point here is that the approaches and those bugs were found by applying intuitively the guidance of this model. And it demonstrates how it can be useful. So the first example here is I'm going to I don't have the specific vulnerability. It was from 10 years ago. I'm just going to find it. Critical infrastructure attack. So in 2014, I participated in a competition at Positive Hack Days named a critical infrastructure attack. Basically, they had this kind of artificial mock-up of a critical infrastructure with various industrial systems, and they had software installed that controlled it. And the goal was to find 0 days and to attack this software with 0 days. And I participated, and I was able to find the vulnerabilities in the Soft Web Studio. So currently, I cannot show. Actually, I think I can. No, I'm going to open my GitHub and just go through the bugs and explain how it works. Here I have this box. So what is in the Soft Smart Studio, the Soft Web Studio? This is an industrial control system, a typical. It looks like it has some user interface and it accepts various inputs. Maybe there are some ports open, whatever. It also accepts project files, which was my attack vector. The project file has a custom binary format. And what I did is I implemented a dump fuzzing of this project format with Radamsa. So first, I'm going to open some test case. It's being downloaded. Here is the analysis. It's super cute. There is a memory copy operation. It's just straight out of the crash dump. It's exploitable. There is not much analysis here. Anyway, so I want to share with you a terminal to take a look at this file so that I can show you how it looks like.
Yeah, I'm always talking on his channel about how memcopy is like one of the biggest problems in the world.
The memcopy is the primary evil for sure. I think I'm going to share the screen in a different way so that I can show the terminal.
Sure. Yeah, that was an excellent first part, by the way. I think a lot of folks were talking in the chat about maths, and how important it is to getting into all of this. So, I mean, it was an excellent introduction there.
Thank you. Okay, I think I'm just going to share the entire screen. So,
Great.
Yeah, looks like it works. I've downloaded the test case.
Could you increase the font just a bit for folks?
Increase the font. How do I increase the font here?
Should just be Command Shift Plus, I think.
Shift plus?
Command Shift Plus.
Oh, okay, it works. I had no idea. So what I did, I just did a hex dump. First, I wanted to do a file test case. It's a sphere cursor screen image. Now, this is definitely not a sphere cursor screen image. This is a binary file of the project of Indosoft Web Studio. And when I do a hex dump, this is, by the way, some skill that I learned during my malware analysis era, that you can very quickly analyze or make sense of the file by hex dumping it and looking at what's inside. You know that files have headers that tells us what type of file it is and so on. So here, there is no particular header. I don't know which file is this, but the file here looks like a typical binary project file. There is some strings. So typically, programs have this kind of files which have a custom format. And when you look at it in the hex dump, you immediately recognize that it's some custom format. It has some sections. It will have some strings inside. Here it looks like some Unicode string. Sometimes it has some binary, which has a very peculiar look that you can definitely recognize a binary based on the hex dump. But here I'm not even seeing any binary code because it's not code. So yeah, this kind of format. Next, what is Radamsa? If you have done any fuzzing at all and you never heard about Radamsa, then this is a shame, really. Radamsa is still around. Radamsa is one of those super universal tools that I always keep in my toolbox. And my personal approach to research is that I always focus on the most fundamental tools. I don't want to waste my time to go through the learning curve of learning yet another, reverse engineering plugin or whatever, unless it is so effective that I cannot forget about it. But focusing on the best tools such as primitive debuggers, GDB, Windows debugger, hex dumpers, objdump, you get the idea. IDA or Ghidra, only the basic tools. So Radamsa is one of those basic tools for fuzzing. And it has been around for a long time. I'm going to just open it in GitHub and talk you through what it does because my current laptop won't even allow me to install it. It is kind of a bit outdated here. So it shows that the last submission to Radamsa was in 2018, which is not good because Radamsa is definitely still useful. So what is Radamsa? It's not technically a fuzzer. A fuzzer is something which incorporates the entire fuzzing infrastructure, meaning that there is a harness, there is a mutator, there is something to detect crashes, something to systematize the crashes and so on. So this is a thing in itself. Radamsa, in contrast, it is a pure mutator. It simply accepts the input file, applies some mutations to it, and outputs the mutated sample. And here, actually, they have an example of how you can build a rudimentary fuzzer on the bash. This is basically what I did 10 years ago when I had fun exploring fuzzing with this. Something like this sample, while true, do radamsa, generate sample, and run our test programs with a sample or something. This is the most rudimentary fuzzer that I think it is very important when you're learning fuzzing is to actually try this kind of rudimentary things. Don't just jump straight to modern fuzzers that are super efficient, because when you do this kind of thing, you will eventually stuck. For example, you use alpha++ and it starts giving you errors. You look at those errors and you have no idea what's going on. You have to rely on developers to answer your questions or in some communities. This is not good, in my opinion. Rather, if you have tried to implement your own fuzzer, this may be lame, this may be not maybe successful, but once you have tried it, you know exactly what is going on underneath. And if you understand the theoretical principles that I explained previously. So what I did 10 years ago, there was no coverage-guided fuzzing. I implemented this kind of fuzzing in the bash with radamsa. And my fuzzer, it wasn't really super dumb because it actually stick together with Windows debugger and with the bank exploitable plugin. So each sample that generated a crash, the crashes were automatically evaluated with the bank exploitable plugin to evaluate exploitability, which I showed in my disclosures repo. And thus I had a very nice directory structure with crashing inputs and automated analysis. So the thing that I showed here is this kind of crash analysis. It was generated, the first part of it was generated automatically by my scripts. And then I added some custom analysis after I took a manual look and attempted to identify the root cause. And this kind of directory structure is also the thing that my fuzzer produced. It immediately says what is exploitable or not exploitable based on the evaluation of bank exploitable plugin. So this was very crude, and it worked. It worked amazingly well. Now back to radamsa. Why is it so good? Radamsa, it isn't shown here. I cannot show you the specific mutations that it has. The power of radamsa is it has a wide array of mutations that it will apply either to the full file or to some section of it. And the mutations are really varied. It's not just like flipping bits or rotating a byte. It also has some sort of high-level mutations that make a lot of sense for fuzzing more complex types of input. For example, if you ever used Affle or any or libfuzzer, you know that they perform their best at binary formats. But as soon as you try to fuzz something which has strings in it, it's a dead end. Absolutely, it just cannot go through some initial test cases. So radamsa actually doesn't have this limitation because it has some mutators that are designed to work with strings, like take out some string from the inside and put it elsewhere in the file, or put some additional values into it or something like that. I don't remember exactly which were the mutations, but the variability, the scope of those mutations was quite powerful, which is why there is a very good list of bugs that was found with radamsa. Another great thing about radamsa is that because it's a pure mutator, you can apply it inside of your fuzzing infrastructure in different points. You can use a standalone, just put in some loop in a Python or in Bash and use radamsa to generate inputs and to feed them to the program, the most primitive case. But also you can use it in combination with more advanced fuzzers and stick it somewhere between different tools. So why is this important in the context of my previous discussion? Because imagine that you have a file which is very large. So my test case size is 29 kilobytes. This is a little bit larger than a coverage-guided fuzzer would like, but it still would work with coverage-guided fuzzing, honestly. On modern infrastructures and with parallelization, it will work. But the thing is, most of this kind of project files nowadays are many megabytes in size. And even coverage-guided fuzzing, it will never, ever discover all of these all of the branches. Because of the where is this? Because of this exponential exposure here, as our file gets larger, the fuzzer has to deal with a very huge input value, basically. So looking at here, the probabilities of hitting a particular branch will be very, very small. The larger the file, the smaller the probabilities. On top of that, because the file is small, because the file is very large, the tree is very complex, and the exponential exposure of complexity that happens here, it will be like unfathomable, which is why it doesn't make a lot of sense to fuzz the kind of multi-megabyte files with coverage guidance fuzzers. And furthermore, if such a file contains strings like the one that I showed here, so obviously this is not a binary file, there is a lot of strings, and applying coverage guided mutations here will not make sense at all. It means that I think this can be proven for real mathematically, that fuzzing this kind of file with Radamsa will actually be much more efficient than trying to fuzz it with any sort of coverage guided smart fuzzer. And for my intuition, I have been able to prove it to myself many times, but I think it can be actually shown. So it's a pity that Radamsa doesn't seem to be popular, as the last inputs of vulnerabilities here are quite old. I think this is part of this fashion of smart fuzzers. It's not because Radamsa is incapable or something. It definitely should be more popular. Okay, now moving on to the next sample. To summarize, despite the fact that this is quite an old example from 10 years ago, my point here is that dumb fuzzing, what is considered a very simple fuzzing without coverage guidance, without any evolutionary exploring of the branches, it can be super efficient. First of all, it can be efficient enough for your particular purposes. And secondarily, it can be more efficient than smart coverage guided fuzzing. Now, the next point, the next example that I want to show you. So here is, by the way, a slide with a summary where I introduce various technical approach to how we can implement this probability density optimization or probability mass optimization in specific technical terms. What I just showed you is one of the ways how we can bring the PF closer to PP is by taking valid program inputs. And specifically, Radamsa is quite helpful for that. The next technique that we can use is generate valid program inputs with context-free grammars. And the tool that I want to reference here is Dharma. Dharma is another kind of super fundamental tool that it's also very old, at least 10 years old, I think. And it's still very actively supported and quite popular. And this tool is genius. The thing about all these tools is that they have been discovered kind of intuitively, empirically. Somebody just stumbled intuitively on this kind of thing that works. And when you look at this model, it becomes so clear why exactly does it work. So by applying this kind of theoretical thinking and thinking forward from it, rather than discovering evolutionary all those tools, we can actually speed up progress in fuzzing. Anyways, the second example that I want to show, how we can generate valid inputs for the program. Recall that as soon as we bring our fuzzer's probability distribution closer to the probability distribution of the program, we start winning at fuzzing very quickly. And this also, if for some reason this is valid, if for some reason you cannot even use a coverage guided fuzzing, for example, you have all the conditions, you have a small file size that is binary, but but your setup doesn't support coverage guidance. For example, there are different systems where I'm not talking about situations when AFL doesn't support it out of the box or WinAFL or whatever. I'm talking about systems where there is privilege boundary, for instance, and where the whole thing is written in a different language, the unfamiliar esoteric architecture. It means that re-implementing coverage guided fuzzing on it will be very expensive, and you need to find vulnerability soon, like in a week. In these situations, also, this is your way to go. So in this example, I'm going to look at a different sample of vulnerability that I found in Microsoft Office. This is also from the around 10 years ago. So I decided at some point to try fuzzing Microsoft Office files. Once again, it was in the time when there was no coverage-guided fuzzing. And even if it was, because Office files are so huge and they are not exactly binary, it doesn't make sense to fuzz Office files with coverage guidance. And the approach that I used here is to try to generate it from scratch. And specifically, you know that this format of docx that was new at the time is actually a zip file. You can unzip it. And underneath it has some XML. I'm just going to try it. To rename docx to zip, and okay, and it created basically inside of this docx is a zip file, and inside of it there is some directory structure, which is, by the way, documented on Microsoft website. You can find the specifications of these formats. This is a bit messy. I'm going to move it separately. So now looking at these files, there is a directory structure, and inside of it are XML files. This directory structure is well defined. It's contained in the specification. And by looking at this, I had the idea, what if I actually, here is it, what if I actually fuzz this? Because most people, when they look at docx file, they try to fuzz it superficially. And what happens if you fuzz a zip archive? If you fuzz this kind of docx file as superficially, the only thing that you actually fuzz is the zip parser inside the Microsoft Word and nothing else. You never get to the actual code of parsing the actual document. Meanwhile, if we do this simple trick, we take out the internals of the doc file and we fuzz them. And this approach turned out to be super effective. So here you can see actually there is some random stuff that was completely very simple fuzzer that I used, just so random. I used a dual approach. First off, I tried to generate the valid XML files for this by following the structure. It wasn't trivial, I must say, because it has a peculiar encoding and schema, XML schema, that you have to follow in order for Word to accept it. And then, aside from generating a valid sample, I also tried to inject some invalid inputs, some invalid data, as you can see here. And this was quite successful. By the way, the fuzzer was also very simple, and the fuzzing rate was, cycles per second was like, cycles per minute was like 60 cycles per minute. Let's say just my fuzzer had one sample per second. by modern standards, this is the speed that's absolutely unacceptable, and it found a lot of bugs. Simply because I applied some smart approach, and instead of targeting the surface, I went deeper and targeted a specific code underneath the surface. In order to generate this, I actually used not Dharma, but some XML generator tool, which I don't remember the name actually. But the idea was simple. The tool took XML schema on the input, and it would output a valid XML file based on that schema. That's it. The idea here is why I'm referring to Dharma, because Dharma is very universal. And there is some issues with my browser.
The demo gods, they always have to do something.
That's why I don't like live demos. And most often I show actually recorded demos, but here I was hoping, because it's just a browser, what can go wrong? I'm just going to stop the screen. Currently the keyboard is not working. I might need to reboot the browser or something.
Okay.
Maybe launch a new browser window. Okay.
Multiple people are asking what the soothing water sound is in your background.
Oh, it's a cat drinker. It's a cat fountain.
Nice.
Yes, it's a fountain. Cats love it, and I love it too, honestly.
Nice. Looking back through some of the questions, because some people had some great questions, but I didn't want to interrupt you.
Okay, I fixed it, and I'm putting back my screen sharing now.
Okay. And for all 3,600 people watching, thank you so much. And make sure you'll follow Alisa and give the channel a follow. I'll post that information up again soon.
Okay. If the questions are relevant to what I'm talking about now, then I can answer them. Otherwise, please keep them until the end for the QA section. So I'm going back, and where I stopped, I had a sample vulnerability, and I wanted to show Dharma.
All right, I see it popping up now. There we go.
So Dharma, as I said, is another super fundamental tool in the fuzzing toolbox, kind of like Swiss Army knife. But its purpose is different. While Radamsa is applying an array of interesting mutations to the large file, or to any file, but for the large files, it makes a lot of sense. Then Dharma actually is able to generate new inputs based on the grammar. And this is super cool because, in fact, it allows you to generate a lot of valid formats, various programming languages, various specific formats. So Dharma is well supported, it seems, and it accepts grammar file. It has some variables internally that allow you to define specific sections of the output. For example, there is some range of values, sections, and why is it cool is because it allows us to bring the probability distribution of the fuzzer closer to probability distribution of the program without gathering any valid program inputs. As soon as you have the technical specification of the format or able to reverse engineer it, you can write a grammar file and start generating inputs that bypass most of this stage of the exponential costly discovery of branches, because you already have valid inputs that most branches, it will just bypass it easily. It won't have to discover. And Dharma is very cool because it is universal. So there are different grammars that can be used. For example, here, let's see. Grammars. Because it is universal, it can be used with different kinds of grammars, and it can be used to generate various types of files. So it has some built-in grammars here. This is not a lot. It does have WASM, which is interesting. This encodes it in high-level mnemonics, it seems. There are better ways of fuzzing WASM, I think. So it has some sample grammars, but because the language is quite simple, so you can easily write your own grammar for a specific file as long as you know the format of that file. And in this way, you can actually improve your fuzzing a lot, and it can be applied to different formats. So yeah, this is also a very old tool, more than 10 years old, I think, and it's still very actively maintained, and it still keeps finding bugs. And I hope that my theoretical discussion shed some light on why exactly those tools became so popular, because they actually solve some problems that usually are glossed over when we're discussing smart fuzzing. So my next example would be less intuitive. We're still trying to bring the PF closer to PP, but now we take a smart approach of reusing existing parser to generate inputs. You can think about it as generative IE. You know that Gen IE is based on the idea of reusing the same analytical A model in the other way around. So you train a neural network. It has some weights inside of it, which allows it to classify things, for instance. And then you basically turn it around and make it to generate this kind of inputs instead of actually classifying them or labeling them. And this is how all of Gen IE works. Similarly, we can do roughly the same thing by reusing existing parser in order to generate a valid format for the file or a protocol. This is an approach which I don't honestly see a lot in security research, but myself, I use it very, very often, and I have used it many times and successfully, especially if you have time constraints and you know that you have some format and maybe you don't know, or maybe you don't have the specification. So you will need to reverse engineer the format in order to generate this kind of sample. And maybe you have the specification, but the format is so complex that it doesn't make sense to waste 3 months on recreating the samples. In this situation, you can simply reuse an existing parser of that format if you have the parser, and let it generate the samples for you. An example here would be somewhat related from relatively recently, from 2018. It's a vulnerability that I found in Hyper-V, Microsoft Hyper-V hypervisor. Attacking hypervisors is a separate topic because you cannot just give it a file. Hypervisor doesn't care about files. It won't parse it. It has its own internal set of inputs. Those inputs are not also usually visible. They are not like calling you out to fuzz them. Usually you have to understand how exactly hypervisor is architecturally structured, which kind of attack surfaces it has, which kinds of inputs, in order to discover the input that you can actually fuzz or trigger a vulnerability. This is, by the way, the fundamental concept behind my vulnerability research courses, which have a very large amount of time allocated to attack surface discovery, attack surface modeling, and attack vector modeling. So for hypervisor, for instance, there is a big model which I had to reverse engineer from scratch from the real implementations to understand what kinds of inputs there generally exist that we can target with fuzzing, for instance. But once we have discovered the input, you can fuzz it. And this particular vulnerability is in a specific protocol. It's inside of a power virtualized device named VM switch. Power virtualized device is actually fundamentally the same as emulated device. It's some device which is implemented in software, except that instead of emulating a real device, it actually implements a totally new device that doesn't rely on input ports or some sort of low-level memory sharing. So VM switch is one of such devices in Hyper-V. It has a very large attack surface, and when you send something from the virtual machine in Hyper-V, it goes through this VM switch. And in order to enable this, because VM switch is a custom device, it also uses custom drivers that have to be installed inside of the guest virtual machine. So what I did is I took these modules which implement the driver for the power virtualized device, and I isolated a certain portion of the code which implemented the protocol, and I put the fuzzer code inside of it and applied some additional optimizations. You know that fuzzing hypervisors is a difficult problem for different reasons that I'm not going to discuss it here in depth, but basically there is no good fuzzer of hypervisors. So what I did is I decided to implement a very simple optimized fuzzer without any coverage guidance, simply based on this kind of analytical optimizations that I discuss in this presentation. Let me open some code to make it more visualizable. So I'm going to show you the code of the driver module of virtual network switch that runs inside of the guest virtual machine, the specific code that I hacked my fuzzer into, and what specifically I did and how did it work. Okay, I need Linux for this. Linux. Because this drivers for Hyper-V are embedded inside of Linux. So I'm going to just take my Linux box.
And I just posted a link up to Alisa's training courses at 0 Day Engineering on the screen if you want to take a look at those. And yeah, I love what you were saying about just because something's old doesn't mean it's bad. There's plenty of amazing tools out there to help you with fuzzing and everything else that have been created years ago, and like you said, are still finding bugs today.
Yeah, actually, all the best tools are classics. All the best things, all the best books, all the best tools are quite old, and it makes a lot of sense because when people are young and they want to take their share of the world, they invent something new and they start to really pitch it like the best thing, which is the reason why in the society we have this kind of narrative that new is good and old is bad, but this is not true. In fact, in most of the real life cases, the opposite is true. So here is the Linux. I hope that you're seeing it.
Yep, we see code up right
now.
So
yeah, so the device that I'm talking about is called virtual network switch, and the specific driver that I was attacking is called R&D's driver. It's like it's not the device driver, but rather it's like a layer over the device driver to implement the Microsoft R&D protocol, which is a different thing. R&D filter, here is it. So basically, Hyper-V has a hypercall protocol, a specific interface which allows the guest virtual machine to talk directly to the hypervisor. This is an enlightened situation when the virtual machine is aware that it is being running under the hypervisor, and therefore it can tell the hypervisor directly what it wants from it. So in Hyper-V, this is implemented through the thing known as VM bus. It's like a universal interface that connects together the internals of the guest virtual machine and various backends inside the hypervisor. There is through VM switch we can communicate to the virtual network switch, to various other device drivers or devices that are implemented in the hypervisor. And how this communication happens is similar to a network protocol. So inside of the guest virtual machine, there is a driver module which implements the protocol. Whenever the guest virtual machine wants to do something, for example, send something over the network, it will send a message in this particular protocol over to the hypervisor. And there is a custom protocol which designs how exactly this communication will happen. And when I saw it, I thought that this could be actually a good target for bug hunting. But because Hyper-V is a binary, finding bugs in this kind of code manually is very unproductive. So I decided to implement a very simple fuzzer. And because I decided that implementing code coverage will be very expensive, so I decided to optimize instead to optimize for the probability distribution of my fuzzer to actually be able to attack something interesting, to find some vulnerabilities. So inside of this file,
sorry to interrupt. Is it possible to increase? Is it possible to increase the font a little bit?
Can I, wait a moment? I just want to finish what I was talking about. So inside of this file, it implements various functions that actually build up the protocol, the sections of the protocol, and then it sends it over to the other side. So my idea was, okay, it's building up the protocol here. So maybe I just can stick the fuzzer inside of it, and it will put in some random values or something. And in this way, I will be targeting a very compact code base inside Hyper-V, which is small. So fuzzer will be quickly running through it. And so here, for instance, now I'm inside of this file, which implements the protocol. And now I want to find some specific code to show how it actually looks like. Okay, here is a suitable thing. So there is some code which builds up a protocol sequence with some values. And this is a very common situation when you have a buffer that has some common value, then it has some length values, it has some additional data attached to it, and so on. The thing, however, the interesting thing about this is that the commons are quite large values. In fuzzing, there exists a problem, a well-known problem, the problem of magic values. Basically, if your program is at some point testing a large enough value, then a smart fuzzer can never discover that value. Basically, the probability is very small that it's almost zero. This is also known as the CRC problem. So here, the values are already large enough. This is 4 bytes, so around 4 million possible values. You can imagine that what is the likeliness that a fuzzer can randomly stumble on this kind of value? It's 1 out of 4 million. This is very small probability. So I decided to optimize for this specifically and allowed my fuzzer to be aware of this kind of values to put it inside of the fuzzing code. And this fuzzer was very successful. It was able to find a vulnerability in, I think, one night of running. And that was my goal. I wasn't aiming to find a lot of bugs. I just wanted to reach some checkpoint. And it also proved to me that this kind of optimization approach is really very promising. And I think it was the first moment when I actually had this idea of this kind of probabilistic modeling of fuzzing. Oh, it was 2018. So my point here, what I show, is that I optimize the probability distribution of my fuzzer twice. First, I reuse the existing parser to target a specific portion inside of the target device. And then I further narrow down and optimize the fuzzer to be aware of the specific common values that are quite large. And this turned out to be the winning combination that was able to find a vulnerability very quickly. Okay, you had some questions?
No, sorry about that. Folks were asking if on the VS Code screen if you could make the font a little bit bigger, but it's okay. It's super crystal clear. I think folks can watch it afterward. But no, it's great information.
Okay. Currently, I have 18% of battery on the laptop left, and I don't have extra ports to connect it, so it's a bit of a problem.
Yeah, it's also quite late for you.
Yes, but no, for me personally it's okay, but in the location, I mean, yeah, it's late.
Yeah.
So I'm going to very quickly discuss some more examples. So I'm wrapping up this first section where we optimize the probability of a fuzzer to bring it closer to the probability of the program. Lastly, of course, here coverage-based fuzzing is the approach that solves it. This is also here it's shown that coverage-based fuzzing is just one of the possible approaches that allows us to apply this kind of solution to optimize fuzzing. The next general approach is to minimize the program, the probability distribution of the program. This can be done, for example, so one example is that you can literally cut out the piece of code from the program and fuzz it separately. This is not new approach. I see it from time to time in security research when people have a large program such as VirtualBox and they want to fuzz a specific subsystem. So they literally cut out the code, they apply some harnesses to it so that it can actually run standalone, and then they fuzz it with AFL or something. This is a well-known approach. And another approach, technical approach for this, is that we can hook inside of the running program in order to loop through only one portion of the code. This is also a common approach. For example, we can use Frida to hook specific function and fuzz the values only in that function. Frida is another awesome tool that I can recommend here. This also shares the same traits as all the other tools. It's very universal. It's quite old. It's powerful. It's versatile. The only negative of the Frida, I think, is that it's quite slow. But in looking at these models, you should already understand how to make even slow fuzzing very effective by optimizing for our other variables. On the side of my samples, I can show, for instance, some bugs that I found in Microsoft Edge. The basic idea, if we want to isolate the amount of code that we're fuzzing without actually carving out the code, we can craft one specific test case that will be targeting a very specialized functionality and just fuzz only that test case. This is a very productive approach, actually. So here's an example with Microsoft Edge. what is going on here? What I did, my fuzzer consisted basically of a script. There was a loop in the script, which I've taken it out from here so that I have the test case. Basically, there was loop in code and there were some random variables here. I had an idea to fuzz some bindings inside the Microsoft Edge, because when a browser connects to the JavaScript engine, there is a distinct portion of code which implements the bindings, and these bindings are usually quite interesting for vulnerability discovery. But usually it's quite difficult to fuzz it in such a way that we target only the bindings and nothing else. So I had a specific idea that I implemented here. The fuzzer was very simple. It's totally running inside of the HTML, no coverage, no saving of samples. I don't need to save samples because when this thing crashes, because it's so specialized, I already know what exactly crashed and what exactly is the vulnerability. This is another benefit from this kind of targeted fuzzing. This bug is, I think it wasn't exploitable for remote code execution, but I think it was worth around $15,000 in the Microsoft bounty. The third approach here is try to optimize the probability distribution of fuzzing to bring it closer to actual vulnerabilities. A very obvious approach here is take one of the past known vulnerabilities and mutate it in some way. In such a way, you will be kind of trying to target the same region of the probability distribution and trying to find similar bugs. This kind of seems intuitive, right? But my point here is to demonstrate how we think about it from the theoretical perspective, because it contains everything. And it allows us to devise new kind of techniques and understand exactly what we're doing. An example here is I can show you in Microsoft JavaScript 9. This is a library that is used inside of Internet Explorer and in some other things as well. It's from 2017. For this bug, by the way, I wrote the exploit, which is in another repo. And it demonstrates remote code execution. But here I'm just going to show you only the basic crash. Actually, it's not so basic here. I added some logic to demonstrate things. My basic idea is that I noticed that Microsoft JavaScript has a particular problem with transitioning from typed arrays, or from transitioning the type of array from one type to another. And during that transitioning, it would easily hit a type confusion. This is the problem inside of the Chakra core engine, which is currently, it's not used anywhere, I think, but it had this problem a lot. So I noticed this pattern. I noticed this bug somewhere. I realized that it would be more popular because the problem appeared quite systematic to me. So I wrote a very simple fuzzer, which once again, it's run inside of the HTML body. There is no coverage, no saving of samples, just running through a specific code which tested various variants of what I thought the bug could be. And this bug was a 0-day. So also this fuzzer was successful. It was able to find the bug maybe in just 1 hour. And it was a 0-day at that moment, but I think that Microsoft wasn't accepting Internet Explorer 0 days at that moment already, so it didn't have any bounty. And also this bug had a bug collision when I noticed that another researcher found it and reported to Microsoft, which also shows that security researchers actually have quite similar thought processes when they do bug hunting. My point with this example here is that we can also apply this in a more systematic way, of course. We can let our fuzzer learn from the past vulnerabilities in one way or another. Or if we're doing this manually, you can take out a sample of the vulnerability, and if you have any reasons to think that it is more or less universal, if it targets an interesting attack surface, then it makes sense to simply randomize some things inside of the test case and just throw it again to the program. and you can quickly find some variants or similar bugs. And the last technique that I show here, it's shown theoretical in the model. Like in theory, we can collapse the probability distribution of a fuzzer to just immediately find the bug. This sounds theoretical, I don't know. But this seems like this kind of thing, it was exactly what happened with my vulnerability that I found for my pound-to-own exploit. I didn't fuzz it, I didn't analyze it. Basically, I just, in the process of research, I stumbled on it or something. This was some of this kind of hypothetical scenario. This is, of course, hypothetical, but my point is maybe if the model shows it, maybe there can be an algorithmic way to do it. Who knows? So these were very simple examples. I think I'm going to stop with the samples now. I wanted to show some more. I wanted also to show an example of how I actually updated UFL and WinUFL to fuzz some things. For example, I used UFL to fuzz VirtualBox, a specific subsystem in it. And I had to implement several things. Eventually it worked, but the problem is that it took a lot of time. First of all, it took about a month of development, and then it took a lot of time in the discovery phase when it was still discovering the branches. Eventually, it did find some bugs, but they were just freshly patched by somebody else. And then I ran out of time on the time budget on this project. So this is how coverage-guided fuzzing can actually fail, because in real life we have time constraints and various other constraints, and coverage-guided fuzzing is better suited for long-running projects like development cycle, where you can just put it and it just keeps discovering things. But in the adversarial games of offensive security, it's almost never works. And my own, this was one of the few fails that I wanted to share, because most of my fuzzing attempts were actually successful, but when I tried this coverage-guided fuzzing, it kind of worked because it found the bug, but it was too late. So it's not suitable for my purposes. I also used WinUFL, and I also had to add some additional logic to it to fuzz Microsoft RDP. And I stumbled on a few interesting things about it. For example, that Microsoft seems to be using some sort of anti-fuzzing techniques that basically force the fuzzer to go astray and not able to discover any new branches. It can be, in this model, it can be demonstrated how exactly it can work and how it can be implemented. So anyway, that approach, it didn't work out at all. Here I showed a very simple examples of how we can use the theoretical model to guide our fuzzing optimization. Of course, they're basic examples, but my point is that we can actually systematize it and make it more algorithmic and build better techniques to do it. And to generalize, we can apply this theoretical model to optimize fuzzing in two ways, on the high level and on the low level. So on the high level is what I just showed. We operate on the scale of probability distributions, and we try to optimize these distributions to target the vulnerability. And on the low level, we can work directly with the branches. For example, we can try to maximize the probability of passing a branch or minimize error rate. This will also be a very good fuzzing optimization. Ultimately, what we want is to reduce error rate, because currently 99% is not good. And there is an infinite number of practical techniques how this can be done, which hopefully I demonstrated a few of them. My laptop's battery is dying. I think I'm going to just close the slides now so that I can plug in the power and you can start asking questions from the community.
Okay, amazing. That was fantastic. Thank you so much. You know, folks appreciate it. We have over 6,000 people on now, so close to the.
Wow.
We're like 200 away from the record, and I think it's going to hit it while 6,500 was the record. It's at 6,300 right now, so it's probably going to be.
Wow, that's cool.
Yeah. So amazing work. I think a couple of the questions were while you were presenting on a specific topic, so the context may be lost at this point. But one of them was, could you explain the mathematics leading to the conclusion there is 1 power to 80 chance to find all branches.
Yes, I think you. Let me find it. Yeah, basically here we have an array of 10 bytes. And because we have an array of 10 bytes, each byte can take a value of 256 different values. So for 10 bytes, there would be 256 to the power of 10. This is obvious. Next, we calculate the probability of that based on the uniform distribution assumption, that it would be 1 divided by 256 to the power of 10. And then through simplification of the powers, it comes down to 1 divided by 10 to the power of 80.
Great. All right, so hopefully that answers the question that was there. So this is another one, context from back when you were presenting about some of your theories. Will this suffer from path explosion, as is the case with symbolic execution?
From, I couldn't quite hear that. From what explosion?
Path explosion?
Path explosion.
Like similar to symbolic execution fuzzing?
So I tried to show here that path explosion is a universal problem in fuzzing, and that even if you are using the smartest fuzzing that you can find today on the market, there will still be a path explosion problem. I don't know how exactly this looks like in the specific scenario that you're referring to, but I think it can be compared. This basically, anytime when we're using fuzzing, we are suffering from path explosion. But the key point here is that currently the best we can do is to contain this. So if we have a particularly bad path explosion problem, imagine that we have an exponential that goes straight up, like almost a vertical line. This is the worst scenario that we have, for example, in this situation, when we have a large array and we just apply dumb fuzzing to it. Here, the path explosion is augmented by the low probability of finding the branch value. And when we're dealing with a coverage-guided fuzzing, what it does is it tries to a little bit put down this curve. So it will still be a path explosion, it still be an exponential trend of loss or whatever. But we're applying techniques that help to contain it and help to control it. And this specific slide helps. It doesn't really. So here, coverage-guided fuzzing, for instance, it solves path explosion problem partially because it solves this branches. You can see that probability here is 1. So basically, when you fuzz with known inputs, you don't have these branches anymore. They literally don't exist. You go straight to the next level, and you have a little bit less branches. But still, the problem exists. So my point is that the best currently what we can do is to control this problem and to contain this problem in various ways. And it is also a very interesting research topic of various techniques that can specifically apply to control this problem, because obviously saving successful inputs in coverage-guided fuzzing is not the only way to solve it. There will be other ways. So this is open research question, I think.
Yeah, absolutely.
Okay, next question.
This one's a bit more high level. I'll pull it up on the screen there for you. Can you see it? It should be on the main screen with you and I on it.
Okay, yeah.
Which is for folks listening, it's besides coverage feedback, what other kinds of feedback do you think fuzzers could use for targets like browsers?
Actually, this is kind of obvious, and I tried to generally explain it in my model. When you have this kind of two probability distributions, the PF fuzzer and the P program and P val, then you can try to receive any sort of feedback from the program to optimize your probability distribution. For example, you can try to record which samples actually produce the crashes. This is kind of obvious, I think. Just record what produced the crash and try to fuzz it more. I'm not sure how many fuzzers actually currently do it, but this is obvious. But yeah, I think theoretically there may be a lot of different types of feedback, but coverage of branches is kind of the most fundamental, because as you saw in my model, the branching of the program is the main problem that we're dealing with, really. We can also apply feedback at a more higher level, like this sample crashed, and this sample, I don't know, maybe executed faster or something like that, but I'm not sure if it's even useful. The branch feedback from the opening new branches is the most important thing here.
Yeah, and so a lot of the questions coming up are ones that Alisa touched on earlier in the presentation. So if you got a little bit late, you can go back and listen from the start, and she addressed a lot of this stuff for sure.
Yeah, definitely.
But this one again, if you want to talk to this one, how do you, like for you personally, how do you go about picking attack surfaces or targets?
How do you pick targets for fuzzing? First off, I want to say that fuzzing is just one of the tools that I use. Actually, I think that all successful vulnerability researchers use a variety of different tools, and fuzzing is just one of them. Personally, I use both static code analysis and fuzzing, and also some intermediate techniques. And fuzzing is just one of them. So if I want to generalize your question and answer it like how do I choose the targets for bug hunting? I don't really choose them nowadays because I like to target the hardest targets. That would be JavaScript engines, browsers, hypervisors, because I know that this is very challenging and this is stimulating. And I think that if I can do it, then it's good both for me and for the community, not for the society. So this is one principle. Another principle is sometimes I just stumble on a program that looks interesting, and maybe I want to try a specific bug hunting approach or fuzzing approach that seems like this program is very well suited for it, something like that. But mostly, of course, I focus on the common suspects like browsers, hypervisors, and so on.
Yeah, one simple way, I've said this in past streams, but that's worked for me, is looking at patch diffs from Microsoft and then taking the vulnerable code that was then patched. A lot of times, if you simply go and hunt for that same line of code as simply as that, you will find instances of that same, sometimes often as like one or as quickly as one or two cross references away.
Yes, definitely. This can be true. And this is actually quite different from one vendor to another, from one software vendor to another. Some software developers patch very well systematically, while others actually, they don't pay much attention to closing the whole class of bug, and they only care about patching the specific vulnerability. And furthermore, the quality of patches is different. So even without thinking about variant discovery, you can sometimes just bypass the patch because it's not good enough. And then even if the patch is good, indeed it is quite common that if the vendor isn't paying enough attention, then you can find variants of the same bug pattern elsewhere. This happens a lot.
Yeah, absolutely. So I don't see any other questions that you hadn't already answered coming up right now. And I know you might be staying up late, but it's pretty late over there for you, and your battery was dying. I'm going to post up Alisa's links again. So we'll start with Twitter. Also on the YouTube video, it'll live on right after we're done here. It'll get posted. Some folks were asking if you were able to share your slides. If you are able to do that, I'll put a link in the description. Otherwise, you can rewatch the stream, of course, and see them there.
Yeah, definitely. I will share the slides. Sure. Why not?
Okay, awesome. And here's Alisa's courses again, if you want to take a look at those. But thank you so much. That was an amazing presentation. And, I know a lot of folks are looking forward to it. Again, we're at 7,500 people right now. So you're definitely quite popular. People learn a lot from you. So yeah.
What's seven? How much?
7,500.
7,500. Wow.
Yeah, it's good. Be surprised. But so yeah, again, if you ever in the future you want to come back on again, would love to have you. But definitely check out Alisa's training and follow her research. And any final words you'd like to share, Alisa?
Yeah, today actually I wanted to show a more technical demo, but I think that I don't have to, show debugging, or everybody knows that I can do debugging and how it can be done. So today my focus was more theoretical, because this I believe is the most important thing that I wanted to share with the community at this point. But in case you were interested in specific practical hacking demonstration or something, if something of I was talking about something and you're interested to see how exactly that can be done, then just let me know and maybe we can organize it somehow, share the video or something.
Yeah, that would be awesome. All right. Well, thank you so much. Enjoy the rest of your weekend, and we will see everyone next time.
Thank you for having me. Bye
Thanks.
bye.
Bye bye.